equation. And let's go ahead and look. Look at the h's associated, the small h's associated with the 6 kilogram mass. So initially, the 6 kilogram mass, using 60 degrees here, means that this angle is at 30 degrees. And so again, at 60 degrees, we have the 6 kilogram mass.
So, Robert?
Yeah.
Why are we not using 180 divided by 2 for this sign?
Well,
Because
anybody want to answer that? Why am I not putting 180 over 2 in here?
Decided 90's one.
Because of what I get interested in is what?
the changing theta? Or generalized?
The more generalized situation for any theta. The question was asking what happens when theta becomes 180 degrees, to get their answer, but I think it's valuable for us to try to, if the problem isn't too complex, to try to just go ahead and write it in its generalized form, so then we have that, we can look at the relationships to see how the variation is going to occur in the energy. So that's why I'm keeping it at theta here instead of just dropping in the 180. Everybody okay so far? Any question? Pam, you okay? Others? Okay. So the 6 kilogram mass at the initial position then, now we have to look at it, and it was sitting up there at an angle of theta over 2 above the horizontal on the lever arm of 0.3, and here was our datum. So it's sitting up here like that, and this is that theta over 2, and so it's above the datum, so its initial H reading, I think that small h, is going to be that sine reading right there, 0.3 sine of theta over 2. And the, I'm sorry, and let me put the 60 degrees in there. So again, sine of 30 degrees, which is half then of this, so this initial height above the datum is 0.15 for that 6 kilogram mass, 15% of a meter. The final position of it at some generalized theta of that 6 kilogram mass is above the datum, and it's positive. And actually I could put a positive up here because to indicate that we thought about it. It's above the datum. And then this one similarly is plus this reading right here with the generalized theta over 2. So we have all those taken care of. Now, back to Daniel's point earlier, noticing that because of the isosceles character, or this vertex angle of theta, and this distance called y, defined as y, then this value in the altitude here is half of the y. See if the math plays out properly. The y was this, on the 4 kilogram mass, was this reading initially, which turned into this, and we should then, and this was the initial, this is the initial on that, and we look over here and see that we have half of it. But again, they're on opposite sides of the datum, so this is positive while this one is negative. we should be able to look here and see the same factor of a half. Feeling good? Okay. Now, what about the dynamical energy, the energy of the motion, the kinetic energy? That involves the speed of both masses. The speed being carried by both masses. The speed of the 4 kilogram mass is what? Called y dot. The speed of the 4 kilogram mass is y dot. So we've got that. And so this term is going to become y dot squared. Now what about the speed of this 6 kilogram mass?
Can we call it half of y dot squared?
Can we call it half of y dot squared?
We're going to need to solve that part out eventually.
Well, that's
Okay.
only the y component of that.
Alfred?
That's only the y component of that. So
Right.
we need to divide it by the trig function of that central.
Yep. See, look at the path. As we keep saying ever since the first week of class, always think about the path being followed by the mass. And the path is on this curved path, and the true velocity, you know, is perpendicular to this 3/10 lever arm. The true velocity. The vertical component, I think you have, is correct. But then you would have to, if you were going to do it that way, everybody with me on that? If you were thinking about this as being the true velocity of this thing, the velocity of that 6 kilogram mass, then the y over 2 is a component, I'm sorry, the y dot over 2 would be a component of that. Just the vertical component. See it? Okay, so you gotta be careful about that. Okay. So now, rather than using, again, let's come back and do using the theta description. If this body is in a circular path about this pivot point right here, then we know that this speed is equal to what? The velocity of the 6 kilogram mass here
Theta dot.
is the lever arm times the derivative of the angle of rotation, time derivative of the angle of rotation, right? Our traditional r theta dot type of thing, but we have a theta over 2 defined for the angle. So we're going to get the r of 0.3 times the rate of change of this, which is going to be theta dot over 2. Theta dot over 2. How does that relate to y dot? Assuming, let's say you did not observe what Daniel had, that this motion was, this height was half of this height. Let's say you didn't have that thought. You did not have that thought. So all you've got is you've got this theta, you've got this y, and you can see, I think you can see that if we would start to build this equation right here, where we have our change in energy on kinetic energy here, and we have a y dot squared here, and over here we're going to put in a 0.15 theta dot squared. Can I tuck that in here? Let me erase the parentheses there. And what we have going on right here is this 0.15 theta dot squared. Have to square that quantity. We need to get the connection between these two, between the theta dot and the y dot. It's easy. It's all sitting here.
Omega r.
Hmm?
Omega r, right? V equals omega, which is theta dot.
Yeah, so what we can do is we can just come down and look at what our y was defined as, and let me tuck it in down here. This y was 0.6 sine of theta over 2. So the relationship that exists between y dot and theta dot is going to be through the derivative of this kinematic relation, this geometric relationship here. So we're going to get we're going to pick up a cosine on this plus a theta dot over 2. I'll just step it through. 0.6 cosine theta over 2 times theta dot over 2. Which is then 0.3 theta dot cosine of theta over 2. So that's the relationship that exists between those two parameters. Now, what piece of information did they give us? Oh, all they said was when theta goes to 180 degrees, what's the speed of, which one were we looking for? The top, the sphere up here. How fast is it going when these arms become vertical? Right? How fast is that thing moving when these arms become vertical? Okay, so let's go ahead and come back on this board and see if I can neatly write then the equations that we've come up with. So our change in energy, kinetic energy on the 6 kilogram mass, the half times 6 becomes 3, and then we're left with 0.15 theta dot squared plus 1/2 of the 4 kilogram mass, which is then 2 times our y dot squared, and then we have to add to it these changes in our gravitational potential, and 6 times 9.81 is close to 60. What is that? 54 and 4, 50 what? 58.7, I'll say, times our small h theta.
58.9.
Oh, 58.9, thank you. 58.9 is the weight of the 6 kilogram mass, and the small h theta was 0.3 sine theta over 2, and we have to subtract from that the initial h on that was 0.15, and then we have to add to that the 4 kilogram mass weight, which is a little under 40, 39.24, and its position at theta was negative 0.6 sine theta over 2, and then we're subtracting from that the negative 0.3, which then becomes additive, and that sum of all those expressions is then equal to 0. Now, we're looking for the speed of this mass at the top. At the top. This is its speed inside this parentheses, isn't it? Okay. So that's what we're looking for. And we need to write that. We need to be able to see how this one relates to it. So how does y dot again relate to this speed?
0.6 or 0.3 theta dot cosine.
Okay, y dot, let's see, where did we do that?
The bottom.
Bottom of this board.
Oh, down on the bottom of the board. So what we need to do, this is what we're looking for, is this thing. And so what we need to do is we need to use the transform on this y dot to be able to write it in terms of this particular speed. So I think it might be worth doing another little calculation down here just to tidy that up. So what we had previously is we had that y dot is equal to 0.3 theta dot cosine of our theta over 2 reading, and the 0.15 theta dot is our speed of that upper body. So if I came in here and took half of 0.15 theta dot, that's the speed there, cosine of theta over 2, so my y dot term needs to be treated as if it's half of the v theta times the cosine of the theta over 2. So that's what I need to use to replace the y dot term. Question, Joel?
Can't you just say that at the bottom of the path? I don't know if you're
Speak up a little bit.
I don't know if you're doing it in general or not, but can't you just say that at the bottom of the path, y dot's going to be 0?
Well, I think we could agree to that from the dynamics or from what we see in the mechanism. But what I wanted to do is I wanted to do this in general for you so that sometimes there are mechanisms, and you may have, I can't remember if I've assigned any, but you're going to have mechanisms where they're not going to be saying at that kind of a condition. So that's why I want to make sure that you know how to, you look at an equation like this, and I want to make sure you know how to play with it in a way to be able to solve. Because right now, looking at this thing, it appears like we've got, with known thetas, it appears that we've got a couple things that are puzzling here in this single equation then. So we have to somehow get them together. So that's why I just wanted to make sure I went through the math with you. I see some furrowed brows.
I'm confused with how does the 0.3 theta dot just go to 0.5 times 0.15 theta dot?
I don't know, did I do that wrong? Oh yeah, I think arithmetic gets me every time. I want, this should actually be a 2, shouldn't it? A 2 factored out here.
So what value did you multiply by that theta dot in order to get that?
What I was trying to do is I'm trying to see this value, I'm trying to see this expression in this expression. And so what I meant to do was this.
Okay, so you numerically recreated what you needed. Okay.
Yeah. So thanks for catching that. Everybody see that now? Okay. So now we've been able to write this speed of the 4 kilogram mass here. We've been able to write it in terms of the speed of the other mass. Then we only have one unknown in our equation. So simplifying that then is we're going to have 3 times v theta squared plus the 2 times this y dot expression being squared, which is going to become 4 v theta squared cosine squared of the theta over 2. And we should be able to tidy these expressions up right here. So why don't we go ahead and clean those up? If somebody with their calculator would take 58.9 times 0.3 and subtract from it 39.24 times 0.6, I just want the sign terms collapse together. These 2 sign terms collapse together.
41.214.
That doesn't feel right. Did you subtract this? This is a little more than half. This is a little more than 20.
That's negative 0.6.
This is a negative 0.6 times 39.24. It's a little more than 20. And we're actually going to end up with a negative there, aren't we?
Negative 5.87.
Okay, so we get a
Yep.
a negative 5.87 sine of theta over 2, and then these numeric terms, this becomes positive here, 0.3 times 39.24. That's positive. And then we're subtracting from it 0.15 times 58.9. 15% of 60 is roughly.
I think it's 2.937.
Positive?
Positive.
Yeah.
Positive and negative on that. And so you ended up with a positive?
Yeah.
Okay. Say again, please.
2.94.
Anybody else get that?
Yes.
Thank you. Okay, so here's a trig equation now that involves v theta. And you'll notice that equation is quadratic. When you factor this out, you end up with 11. Oh, I'm sorry, you can't do that. You can just factor out the v theta squared. So if we factor out the v theta squared, we're left with 3 plus 8 cosine squared of theta over 2. And if we take these other terms to the other side of the equation, they become positive 5.87 sine of theta over 2 and minus 2.94. So the v theta term in general is going to be equal to a messy looking square root here, which is going to involve the terms on the right, 5.87 sine of theta over 2 minus the 2.94, and inside the radical in the denominator is going to be this 3 plus 8 cosine squared of theta over 2. When we put in 180 degrees, we should get the answer the book has. It's going to be approximately equal to 5.87 minus 2.94 divided by 3.
Yeah, it's pretty close. Oh, wait.
Yeah, they're pretty close.
Point
Maybe
99.
976 if you want to.
What'd you get?
Oh, you got to square root that.
Oops.
It's 0.99. Yeah. 0.99.
There you go. 0.99. And the units on that should be meters per second. Is that right? Okay. Now, why did I spend all this time playing with carrying theta for the generalized position? I wanted to get to this point so that we could now do what? Not just drop in the 180 and pop out the answer, but draw a sketch of this velocity as a function of variable angle theta. So what I'm going to do is I'll take just a moment to kick this into the calculator, and we should end up then with a graph of v theta as a function of theta, and when theta was 60 degrees, we should have v theta being 0. And then when we get to 180 degrees, we should see a value of 0.1 or 0.99. And is doing something in between there. So if you'll just bear with me for a second. I'll key this into the calculator.
All math breaks from negative phase.
So here's the equation. I had to nest a bunch of parentheses in that to be able to make sure that the whole thing stayed inside the radical. And then that the numerator was nested in a parentheses, and then the denominator separately is nested in a parentheses, and then I also have to be careful with the squaring of the cosine. So I did that, and then I built the following viewing window in degree mode, 0 to 180 degrees at 60-degree increments. And then vertically, I knew the velocities weren't very great, so I set these vertical elements for the window. And then the graph is this. So if I turn on trace and I go to 60 degrees, I get an undefined value. But if I move microscopically off of that to, say, 60.1, we're getting a 0 reading. Oh, what's going on there is it's because of us rounding off those values in our work, and we're getting a radical that is negative right in those values near there. If I just get over here just a little bit on the angle, you can see that we're at the 0. And then if we go to 180 degrees, you can see there's our reading. And again, we had approximate values coming off, that we used in our calculator here. So that's the reason we're at 0.98 instead of closer to the 0.99 value. Excuse me?
From 0 to 360, gives you a nice graph.
Okay, and then of course this is a radical, so it only will draw it for us under real values with this calculator. So you suggested going to 360 on this, and let's see if that mathematically is going to let it do its thing. It should probably just arc up and over. And then it would become undefined. Okay. So the mechanism is that arm, that thing is going to do this. It's going to do this. Well, actually, this part down here is vertically going down. But then it's got motion, doesn't it? That bottom body had stopped. But that upper one is moving horizontally. And so then that's going to start pulling that lower one back up because it's got some speed as it goes through the top. So that momentum it's carrying is going to cause that other one then to come back. And you can see then in the curve here that the thing would just act as an oscillator. It just act as an oscillator.